Okay, the calculations in this are based on problem 2 of the ANOVA activity sheet with the pricing strategies and the sales of the green beans. I'll let you just read this first slide. Okay, as I said on the last slide, we have all 15 numbers in the data set now instead of dividing them into groups. There they all are. Add them up, 135 divided by 15, that's 9 for its sample mean. Subtract that 9 from every value of x and you'll get the deviations, the x sub I minus x bars. Then you'll square those to get the squared deviations, the x sub I minus x bar squareds. And then you'll sum those up. That's where I have this 274 from. That's just like what we've been using in the numerator for our calculation of standard deviation all semester. So that's what the sum of squares is. It's just the sum of squares for the whole data set. So SST, sum of squares total, meaning it's for all of the data. Now what I'm going to do is get sum of squares within each group. This is going to end up being sum of squares error. So in group A, I just get the x's, the mean for that group is 5, subtract 5 from each of the values there, square those, and get that sum of squares. So that's 30. Again, that's the sum of squares just for group A. Then do the same thing for group B, then do the same thing for group C. Add those up and we'll have the sum of squares just for the errors. This is within the group. So when earlier in one of the other segments we were looking at in one of the visualizations what happens when we change the variability within the groups. This is the measure of that. When we change the variability of the groups, we change the SSE, the sum of squares total. The mean square error then, at least one formula for it, using the sum of squares, take that sum of squares, divide it by the degrees of freedom for the denominator, and you'll have, so 144 divided by 12 is equal to 12. So that's the mean square for the error. You may remember that degrees of freedom denominator was total sample size, which in this case is 15, minus the number of groups, which is 3, so you have 12 degrees of freedom. Remember before in one of the other slides, and actually in several of the other videos that I have produced here, we've calculated MSE as the average of the sample variances. In this problem, the variances were 7.5, 16, and 12.5, and we just took the average of those to get 12. Just two different ways to get to MSE. You might want to pause on this slide and just kind of make sure you understand where all these numbers are coming from. I'm going to give you a little bit of a visualization here. We'll look at this again in a couple of weeks in a little bit different context. In this particular thing, what we can see is that we have the sample mean, and then all the blue points are just individual values. So you can see the mean is in between that. It looks like it's around 59 or something like that. Kind of get in your mind what this is. We have all these different points, starting over the left, maybe somewhere around 35, and the next one maybe around 48 or so. Have all of those points, and then we have the black line across the middle that's just the sample mean. So this would be a data set then with about 7 values. Now, the lines on this indicate the deviation. So if this was an X, or let's just say it was Y, since it's going up and down. If we were doing, each one of these points would be Y sub I, the bar would be Y bar, and so you would have each one of these deviations is Y sub I minus Y bar, or just the deviations like we've had when we've calculated means and standard deviations from the past. If you want to call that X and X sub I minus X bar, that's fine. course, the sum of those deviations of those distances from the mean is going to be 0, as it has been in previous calculations. So we had the x's. That was the slide before this. Now we have the deviations, the x of I minus x bars. Now we square those deviations. So I'm going to get into a little bit more of a geometrical kind of picture of things. When we have been getting those deviations, those you could just look at those as just lines or distances from the mean. Now we square them. We have squared deviations. This is each one of these boxes on here is an x sub I minus x bar squared, or a y sub I minus y bar squared, whichever symbol you want to use. But anyway, you get all of those squares, add them up, and you'll have the sum of squares. So when we had the numerator for our calculations of standard deviation and variance, that's what we had was the sum of the areas of those squares. In this case, since we're going away from the average, this would be the total sum of squares, like the one where we had the 15 numbers a couple of slides ago. Well, it turns out if we took that total sum of squares, in this particular problem, the problem we've been doing about 3 or 4 slides ago, we had all 15 numbers, we computed sum of squares total, we had 274. Then even more recently than that, we've computed SSE, we got that to be 144. Now we want to get the sum of squares treatment. One of the things we could do is just take that 274 minus 144 to get 130, because the total sum of squares is going to be composed of 2 things: the sum of squares treatment and the sum of squares error. So what we've done is taken that total error that we had in the whole data set and said that we can divide that into 2 components. Some of that sum of squares is sum of squares that we can associate with the treatment, with the group we're in, A, B, and C. And some of the other slides we had like X bar 1, X bar 2, X bar C, and we had some graphics and so on. This SSTR is looking at the differences between the X bar 1, X bar 2, and X bar 3. And the sum of squares then is the error around each one of those individual means. The other thing you can do if you want to look at SSTR and just kind of put all these things together, SSTR, the sum of squares treatment, was also the numerator when we calculated mean squares treatment in an earlier part of this presentation, or another earlier segment of this presentation. Just take another look at the geometry of the sum of squares. If we think back a few slides ago, and hopefully you have this written down somewhere, we had the 15 numbers, the deviations, the squares of each deviations, and we had those up, and we had 274. So this whole area of the square that I have here is the 274. It's the sum of those squared deviations. We can divide that up, let's set them to go into 2 portions. The sum of squares treatment, which was 130, and the sum of squares error, which was 144. There's another measure, and it is the ratio of SSTR to SST. So SST is the whole box, and SSTR is about half of it. So if you took 134 divided by 270, you'd get something called eta squared. This one is more how much of the total variation did we account for. So we started out with 274. We've accounted for 130 of it. So I think if you calculate that out, you're going to come with somewhere around 0.46 or 0.47. Anyway, we've accounted for about 1/2 of the original variation from the sample mean. We're going to come across this again when we get to linear regression, and there it's going to be called R squared, or the coefficient of determination. And I'll actually go back to the graphic we had a minute ago, and I'll be able to give you a better sense, because actually that graphic was made for regression, and we'll look at this again. But anyway, this is a measure of effect size, and it's of the total variation that we had, how much of it is accounted for by our independent variable, or treatment in this case. And then just remind you that the F-test was take each of those, divide by its degrees of freedom, and you'd have MSTR divided by MSE. I'll just let you take a second to read this. You have the source for each area, so we have the treatment. That might be whatever, if we go back to the study on the green beans, which we're doing now, that is how much is due to the fact that we have this pricing strategy versus this one versus that one. Error, that's remaining error, and then total, that's just the total error if you didn't take a treatment into account, just sum of squares around the mean of all of the data. Then you have the degrees of freedom for each one, and then when you divide sum of squares by its degrees of freedom, you'll get mean square. I'm not going to really put this on an ANOVA table, but if we did 274 divided by 14, that would just be the variance for the whole group. And we have sum of squares divided by n minus 1. Then the ratio of mean square treatment, 65, to mean square error, 12, is 5.42. That's the f-test that we calculate. Then over on the far-hand side there, I put eta squared, which is 474 in this case. I'll have to tell you that you won't always see eta squared over there. It's, I think, a movement to say let's always have it there, but I'll have to admit that you won't see that everywhere yet. What we'll do with the p-value, and the reason I highlight it in red, is we'll use calculators, computers, statistical software to get the p-value. We won't actually compute that ourselves. So just to summarize, sum of squares treatment, that's the 130, plus the sum of squares error, that's 144, is equal to the sum of squares total of 274. Let me come back and just reiterate that you're going to see this table a lot, and you can of course expect a few questions on upcoming assignments, quizzes, exams, and so on. Recall that the degrees of freedom for the numerator was k minus 1. So if we had 3 groups, 3 minus 1 is 2. For the denominator, it's the total sample size minus k. If we had 15 for our total sample size and 3 groups, that's going to be 12 degrees of freedom. And then the degrees of freedom total is total sample size minus 1. So that's where you got the 12, the 2, the 12, and the 14. You can note also that not only did the sums of squares add, but the degrees of freedom for each one add as well. So the 2 plus the 12 is going to equal 14, and you'll always have that relationship. So one of the things with this table I want you to focus on is how are the different values related to one another. Okay, just MSTR then, just reiterating here, 130, the sum of squares treatment, minus 2, the degrees of freedom in the numerator, is 65, that's the mean square treatment. The mean square error, I actually should have put that up here, but it's sum of squares error divided by degrees of freedom for the denominator will give you the mean square for the error, MSE, that's the 12. Then if you take the MSTR, the 65, divide the MSE, divide by MSE, you'll get 5.42. I know this is repetitive, but well, I also know it probably needs to be repetitive. And then eta squared is just the ratio of SSTR, the 130, to SST, the 274.